Saxon Advanced Mathematics, Lesson 64. The lesson that I'm about to teach is mathematically super easy. The actual calculations, the calculations that we're going to do are super simple, super easy. You'll be like, what are you even talking about? This is so easy. What is difficult about this lesson is I'm going to blow your mind a little bit with some ideas, but mostly it's the notation that makes most students' head flop around a little bit. But trust me, it's going to be fine. Here's what I want to tell you. We've been talking about rectangle. Let me just make a little chart. I'm not sure how long I want it to go down. Okay, so this column is a little narrower. These two are meant to be about the same size. We have been talking about rectangular and polar forms of numbers. And just to use a simple example, we have written this as two. Let's just pretend this is something that we have been working with. Or this is just an example, sorry. Right? We've been using this R and U format, right? Where this is how many units to the right, this is how many units to the up, if you will, right? This is the x-axis, this is the y-axis. We can put minuses here if we need to. And then we've also said that you can take these very same coordinates and write it in a polar form, where this is the angle, the direction that you travel from the x-axis, right? We always start at the x-axis and go back that way. This is 30 degrees, is how far you travel. And then 4 is the distance out from the origin, right? So distance and direction. These 2 points, these 2 notations will get you to the very same point, and that's kind of the majesty of the whole system, right? As you can go back and forth between them. We call these vectors. We haven't really used that word a lot because this is the only thing that we've been talking about. We're going to introduce a second category of ideas that we're going to use these notations very similar to these two. Now, let me just tell you one other thing. Some mathematicians, instead of using the R and the U system, like to use, the numbers work exactly the same, but they use an I and a J instead of the R and the U. And in that case, they refer to the x-axis as I and the y-axis as J, right? So in either case, this is the x-axis and this is the y-axis, right? Okay, and we don't have any such distinction. Polar form is just polar form. It's always the same. Now, here comes the little kind of mind trippy part. That's the first category. And here, let's do this. Draw yourself another row. Go ahead and extend the columns. Here's the mind trippiness. We can take our same Cartesian coordinate system, this, and we can use it to graph complex numbers. Okay? Now, what happens is that we always put the real, remember a complex number is a plus bi. We always put the real part, the real number, that goes on the x-axis, and we put the imaginary part on the y-axis. Okay, so real, imaginary. That seems logical, right? Because we always think of the x-axis as being first, and the real part is what comes first in a complex number. And we always think of the y-axis as kind of being second, and that is the second part that comes. So that kind of makes sense. So we can graph imaginary numbers on the same system. We usually call it the complex plane if we want to use it for graphing complex numbers. If we're doing just regular numbers like vectors, if you will, we usually call it the rectangular coordinate system or the Cartesian coordinate system. You've probably heard those names. We just call it the complex plane when we're using it for this purpose. Where it gets wonky is when we straighten out the notation. Okay. So we're now going to talk about how we graph complex numbers. This is the part that's weird. Assuming that it's the same set of numbers, we would write it as 2 square root of 3 plus, no, I'm sorry, not this. I'm using the same numbers as here. Now look what happens. Real and imaginary, that's the format we're used to. But what happens if we compare it to an author who's using this style of notation? Here, the I is on the first part. Here, the I is on the second part. Isn't that monstrous? It's super confusing. So we just have to know, as mathematicians, that if we see the I on the first component of the expression, then it's probably a vector, and we're using the I and J notation. But if we see the I on the second component, then we have to go, oh, this is actually a complex number that we're graphing rather than a real number vector. Ay, 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 ay. That's a little nutty, isn't it? Things get even crazier when we go over here because there's really no way to distinguish between this and what we would like to use for graphing the polar form of a complex number. So mathematicians have had to get a little bit creative to come up with another way to write this. Even though this is so close, they had to come up with some ways because they didn't even have two different ways for this, for the polar form. So this is what mathematicians came up with. They said that you would graph it as 4 times the cosine of 30 plus I times the sine of 30. Now, this looks really confusing at first, but we know that it makes sense because we know that to find the polar form, you use cosine to find the first part multiplied by the hypotenuse, and you use sine times the hypotenuse to get the second part. That kind of makes sense, but look how long and cumbersome that is, right? This is another way of helping us make a distinction between this format and this format. And we know that this makes sense because we use this kind of calculation when we're converting back and forth between polar and rectangular. We've done that. We know that multiplying cosine and then sine, and we know that sine would be on the imaginary part, right? Because sine gives us the up and down measure. So this kind of makes sense, but it's so cumbersome. So instead, what mathematicians have agreed upon is to abbreviate this. And we write 4 cis 30 degrees. What? It seems so confusing. But all we're really trying to do, we meaning mathematicians, is we're trying to find another way to write polar form coordinates when we're talking about complex numbers, because if we write it exactly the same, then no one will know whether we mean complex numbers or polar form. So what I want you to do is just to get used to recognizing these two presentations, especially this one. It simply means do the same work that you do for this, only recognize that you're working with the real and imaginary numbers rather than just standard vectors. That's all it means. So they operate in exactly the same way. We just note them in a different way. Oh, it's so weird, right? But we'll get used to it, and you'll look at this and just see that in your head, right? It'll be the same. Now, so this represents the direction, and this represents the distance, and this CIS thing, which stands for cosine plus I times the sine of, this is just your big fat clue that it's a polar coordinate for complex numbers. I'm writing really small. And I'm going to use that hashtag sign that used to mean numbers. All right? So you'll almost substitute in your head directly to this. It's kind of like when we see radians, we just go, oh, multiply it by 180 and you'll be fine, right? 180 over pi. The same thing will happen with this. Now, all we're going to tackle in this lesson is how to multiply numbers when they're in this format. Why would we want to multiply numbers when they're in this format? We don't know yet. But we can take the polar form of a complex number and multiply it really easily. And so we're going to do two problems to illustrate that. That was the mind-bendy part of this lesson. This is the calculation part, and this is easy. All right, I'm going to write it out the way John did for 64.1 because it's long and cumbersome and it looks really scary. And then I'm going to show you that it's not. All right. Grace is being very dramatic. Pretend this is all one line. Okay, we're supposed to multiply this. Lord have mercy. And we can see, okay, this is one big chunk. And then this, pretend it's connected, is a second big chunk. We're multiplying those two together because it's brackets and brackets. But what is all of this? Oh, wait. As soon as you see that cosine plus I sign, you realize, oh, it's this. That's how this is formatted. So we can rewrite that big long train of ugly into this. See how I did that? I recognize that this pattern is the notation that we use like this. There it is again. Cosine plus I sign, right? That's what the CIS stands for. Then we grab the number at the front, that's the hypotenuse, and we grab the degree measurement at the back, and that's this. Oh, now that looks like something we can manage, right? Now, here are the rules for multiplying. We multiply the distances and we add the angles. Okay, that's our rule of thumb. And this is so easy, you'll love it. Multiply the distances, that's the 5 and the 6, so that's 30. And then we write the CIS, the notation, and then we add the angles. And that's the answer. Now, you may be asking, but why would we want to add the polar form of complex numbers? We're not going to talk about that, but this is a tool that you will use in more advanced classes to manage these calculations. All right. So let me just show you one more. So in this one, you had to recognize that John was using the long, cumbersome notation, and you could simplify it down to this, and then it looked manageable. In this second one, John is giving us the nice, short version. Second, that was the right answer. I didn't mark that. Okay, so this one, he's giving us the notation that already is starting to look a bit like a friend. Again, remember the rule is multiply the distances, the hypotenuse, right, these. And sometimes John refers to these as the absolute values. And that kind of makes sense. We know that the hypotenuse never has a sign, plus or minus. We've never used that terminology before, but if he's talking about the absolute values and the angles, you know that the absolute value is the other one, right? So again, we multiply these and we add the angles. A little trick I've developed to help you remember. Oh, this isn't quite the answer. Let me help you with that in just a second. You wouldn't want to multiply these, right? That would be ridiculous. So that helps you remember, oh yeah, the bigger numbers you add, the smaller numbers you multiply. This is correct, but this is a value larger than 360. So we want to notch that back so that we're not spinning extra times around. You know how we hate to spin extra. So it would be 35 at, what would this be, 220 degrees, right? That's the correct answer, okay? So if the angle you create is more than one spin around, subtract until you get it down to a first order angle. 35 at 220, that's correct, okay? I'm gonna write reduce to one spin. I hope that makes some sense to you. But those are the 3 steps for multiplying the polar form of a complex number. What? Okay, we're off and running on the complex plane. We're going to add to this, but there isn't really a lot that we don't already know. What John's going to do, though, is all of the problems we've been doing. Let me just go back to this page. All the problems we've been doing in going back and forth between these two, he's now going to toss in problems going back and forth between these two. It's the same math. It's just different notation. And then he's also going to torture us with this I and J thing. Again, if you see the I and J, you know that's rectangular. If you see just the I and it's on the second part, that's your clue that it's a complex number. I hope I didn't fry your brains out. I hope that was kind of like, okay, sure, we can go along with this. But yeah, that's lesson 64. We'll talk about it on the video chat. Let me know how your brain is doing, and hopefully we will survive this and be on to greater things. Goodbye, students.